Good mornings everyone. In the series of our lectures on operating system, we have covered up various components of operating system where we started with the CPU scheduling. Now, we will try to do some of the algorithm which are associated with the CPU scheduling. Now, there we are going to cover up basic concepts, scheduling criterias and scheduling algorithm. That is what we will be covering up today. Now, once we say we are to schedule our CPU, what exactly we are trying to do is we would like to maximize our CPU utilization, that is the number of programs, the number of processes which I can execute within a unit of time, that should be maximized, and we say it is with respect to the multi-programming. Now, once we say we would like to optimize this CPU utilization, that is the amount of a job which can be executed on a CPU, that should be maximized. It may be because if I look at our jobs, they are in terms of the IO burst cycles or CPU burst cycles. What do we mean by CPU burst cycles is the amount of a time it takes to execute few instructions before it goes for the input output. That is what we call as a CPU cycle or the IO burst cycles. Now, once it goes for the IO, then obviously it has to wait for, what is it waiting for? The moment it completes its IO, as we discussed in our last session also, it has to go to into the ready queue, and from the ready queue again it gets the CPU burst. How does it get the CPU burst? The moment it has completed the job which is running on the CPU, it is complete, then next job gets the CPU burst over there. Now, basically once we say we are to schedule our CPU, we have to schedule this CPU burst distribution. Okay, how many bursts my CPU will be requiring, my process will be requiring to execute on the CPU. This is what we are to have once we say we are going for the CPU scheduling. Now, if I look at my execution of a job, maybe initially I will be loading my load store or I will be processing it. Now, let us say we are loading, we are adding, we are reading from the file. Now, at that particular moment, the moment I say we are reading from the file, my IO burst will start at that particular moment. Now, in this particular phase, my job is going from CPU burst to the IO burst, and at this particular moment maybe my IO burst is starting. Now, at this particular moment my CPU is idle and it is waiting for this particular IO burst to be over at that particular time. Now, then let us say we have got few instructions, we say load, we say add, then we go on for the reading of a file. The moment we say read a file, it has gone for the IOs and my processor is waiting for the process to come out of the IO there, and this particular phase we call as the CPU burst. Okay, in this particular amount of a time, my process is gone for the execution purposes. Now, the moment it goes for the IO, we go for the IO burst over here. Now, if I look at my jobs, now basically they are a combination of a CPU burst or the IO burst. So, this is what we have got as a job. So, over here this is what is a CPU burst, this is IO burst, again CPU burst and again IO burst. So, basically what it is getting is over the time it is getting a sequence of CPU burst and the IO burst till the time my job is complete. Now, in case I have got a single user system, then maybe at this particular moment my CPU is idle. But the moment we think about the multi-programming, at this particular time I will be loading some other job into my CPU there. I think this is what is the basic concept once we are to execute a job in terms of the multiprogramming there. Now, at this once it loads another job at this particular moment, now this job start executing its steps. Now, my one job has gone for the IO, another job is executing. So, like this it is a sequence of this sort of a jobs which keeps on coming, keeps on going to the CPU and executing the steps, and again they come back for the IOs there. Now, this is my histogram of the CPU burst time. If you look at the frequency and the burst duration, now initially maybe my frequencies may be very high, but my burst duration milliseconds they keep on decreasing. Now, who does this sort of a things for us? There is one thing known as CPU scheduler. So, what is the function of this CPU scheduler? It just selects out of the processes in the memory which are ready to execute, it selects one of the jobs and allocate it to the CPU. Now, then if CPU scheduling decision which are taken at that particular moment are, maybe we are switching from the running to the waiting state, that can be one sort of a decision which we will be taking, or switching from the running to ready state, that is my job is in the running state, but due to some reasons I had to take it out from the CPU, or it switches from the waiting to the ready state. Okay, it was in the waiting state for some IOs, but now it goes to the ready state or it terminates. So, these are some of the ways, some of the points where it has to decide whether some sort of a scheduling has to take place or not. Now, if I look at this 1 and 4, this 1 and this 4. So, this is at the time the job wants to get into the getting out of the CPU. We say it is the non-primitive states, that is job of its own wants to get out of the CPU, and there is nothing which is being forced upon him to come out of this particular job, and all other scheduling we call them as a preemptive. What is a preemptive? Preemptive is in case I got a job, there is maybe I can explain you. Okay, let us say there is one job there, let us say there is a job which is there in the memory, let us say this is my OS, this is my jobs P1, P2, P3 and P4. Now, let us say this is my CPU which is executing this job, because this preemptive and non-preemptive is a very important concept. Okay, the moment let us say this P1 has gone for the execution. Now, the moment all the steps of P1 are over and it terminates, then we say it is a non-preemptive, meaning P1 job whatever instructions were there in P1 that are over and it has been terminated, or it goes for the IO, that is some IO has to take place, it goes to the IO, and at that particular case let us say there is some IO device for which there is some queue over there. Now, it goes to that particular queue and processes it. Now, in these two situations we are not forcing the job to go out of the CPU, but the process or the job is going off its own. We say my job has been terminated or it has gone for the IO. We say this sort of a taking out of the jobs from the CPU as the non-preemptive. Now, another thing is let us say this job was there on the CPU, but it has been taken out from the CPU due to some interrupt or due to some reasons. Then in this particular case we say this is a non-preemptive. Maybe we will go through in details. Okay, let us say there is a job which is executing it is steps, it is not to terminate, it is not to go to IO, but there is another process which comes over there, which is of higher priority. It's just like you go to a shop, there is one the shopkeeper is showing the things to someone, then the moment some other customer comes, in case shopkeeper keeps on showing you the things till you are satisfied, we say it is a non-primitive. But the moment he starts showing the things to the next customer, why he is showing the things to the next customer? Maybe he is the most important to him, he is a regular customer to him, or he knows he will be purchasing much more as compared to the existing customer. So, that sort of a thing we call as the primitive scheduling. Primitive is you are being forced to vacate, that means CPU is being the process P1 which was executed on the CPU has been forced to vacate for some other job. We call that as a primitive scheduling. That means, it has not completed a thing, but it has to be forced to vacate that particular place. So, as I said, in case I have got a 1 and a 4, they are the states which comes of its own, we say they are the non-primitive, and state 2 and 3, there are some 4 states, we say they are the primitive schedulings. Now, then we have got another module there, which we say it is a dispatcher. What is the function of the dispatcher? It gives control of the CPU to the process selected by the short term scheduler. As we discussed earlier, okay, there is one short term scheduler. What is the function of the short term scheduler? It takes the job from the memory, puts into the CPU. So, this is the dispatcher module which gives the control of this particular process for the execution to the CPU. Now, what are the things which are involved over there? Maybe it has to go for the context switching, meaning one job which was already there has been taken out and new job has been loaded. So, this involves this, or switching to the user mode or jumping to the proper location. One is when we get this sort of a state where it has to jump to the proper place where it has to restart. In case I have got a job which was in execution, but is taken out for IO, then what it has to do is it has to execute from the steps where it was last left. So, as we discussed, there is one PCB block through which this information is again loaded onto the CPU for this particular function. Now, there must be some gaps once a job is there and it start executing after the first job has gone from the CPU. So, that sort of a latency we say is a dispatch latency, meaning thereby there is a time it takes for the dispatcher to stop one process and start the other process. What are the things which are involved once one process has to be stopped and another process has to be loaded? Maybe you have got some information in a PCB block which has to be saved for the job which you are taking out of from the CPU, and there may be other job for which there may be some PCB information which is lying at the PCB block, which has to be again loaded into the CPU there. So, that at that particular moment my CPU is not executing any part of my program, but it is just doing some sort of a housekeeping jobs. So, that is what we call as a dispatch latency. Now, question arises, what should be my criteria for scheduling? Because I must have got some criteria through which I will be able to say, okay, these are some of my criteria based on which I will go for the scheduling. Now, basically what exactly we wanted to do is, for most of the time my CPU should be busy. How can I keep my CPU busy? In case I can assign every time my CPU is free, I should be able to assign him some job. So, that is what my criteria is. Maybe first criteria is I would like to have the CPU utilization, keep the CPU busy as much as possible. And next, what should be my next objective? I should be able to execute as many number of jobs as I can. So, that sort of a thing we call as a throughput. Throughput is the number of processes that completes their execution per unit time. Okay, in a given unit of time, how many jobs are completing their processing, we call that as a throughput. As we discussed earlier, in case I have got a very small job, a 1 second job vis-a-vis a job which is of 30 unit of a time, then in case I can load this particular job first and execute it, maybe that will help me increasing my throughput there. Or then the turnaround time, that is the amount of a time to execute a particular process. Okay, once it was submitted and how much time it gets a turn for the execution, that is what we call as the turnaround time. Or the waiting time, okay, amount of a time a process has been waiting in the ready queue. Or response time, this response time is with respect to your online systems. Okay, the amount of a time it takes when the process was, when a request was submitted until the first response is produced. But we do not say it is output, it can be the intermediate responses which are coming over there. Maybe in case of a time sharing environment, this response time is very important. Now, these are some of the criteria based on which we would like to go for my CPU scheduling. Okay, CPU utilization, throughput, turnaround time, waiting time and the response time. Now, what is my optimization criteria? I must be able to maximize the CPU utilization, okay, the amount of a time. Ideally, I should be able to have a 100% utilization, maybe 100% utilization is not possible, maybe we go for let us say 80% of utilization, that is the most optimal thing which we can think of, and we would like to maximize the throughput. Maximize throughput, number of jobs which it can execute, and minimize the turnaround time, minimize the waiting time and minimize the response time. Maybe I have to maximize CPU utilization and a throughput, and I have to minimize turnaround time, waiting time and the response time. So, this is my optimization criteria which I must follow once I had to go for my CPU scheduling there. Now, then there are algorithms through which this particular thing is being done. We have got a simulations of those sort of algorithms. We say first algorithm is first come and first serve basis. That means, whichever job has come first for the CPU utilization, I will be executing them first. Let us say there is a job P1, it may need 24 unit of a time, burst time, it may P2 it needs 3 and P3 it needs 3 unit of. Let us say we assume these sort of 3 processes which are to be executed, and let us say they all come in this particular order P1, P2 and P3. Now, how my Gantt chart will look like in this particular case? Let us say I start at this particular 0 event and up to this particular time my P1 process is getting executed. Now, the moment my P1 job is over, my P2 job will be starting here and it will be processed, and then P3 job will starting and it will be executed here. So, this is what we have got the scheduling timings which will be there for this sort of processes. Now, what can be the waiting time in this particular case, because that is very important, how much I have to wait for in a particular scheduling algorithm. Now, in case I look for P1, now P1 the moment it has come, since there was no job which was executing on the CPU, it will not have any waiting time because it started at the 0 point only. So, this is what P1 will have a 0 and P2 once that particular job is over, maybe it has taken 24 unit of a time, then P2 will start and then it needs 3 unit of a time, at 27 unit of a time the third process will be starting. So, so this is what we have got. Okay, P1 will have a 0 waiting time, P2 will have 24 waiting time, P3 will start at this particular moment, it will have a 27 unit of a time which is required to wait. Now, what is the average waiting time in this particular case? Maybe if I sum up all this divided by 3, this will be my average waiting time in case I have got this first come first serve basis. Now, what do you observe in this? Let us say a job is there which requires 24 unit of a time. and there are other jobs which just require only 3 units of a time. So, maybe my job which is requiring 3 units of a time, it has to wait for 24 units of a time before it gets turned for the execution. That is the reason why this particular waiting time is, average waiting time is more in case of a first come first serve basis. Now, let us say in this particular first come first serve basis, my order of the jobs is very important. Let us say they do not come in this particular order P 1, P 2, P 3, but let us say they come in this order P 2, P 3 and P 1. That is, initially P 2 job came, then P 3 job came, then P 1 came. So, if I just draw their Gantt chart, maybe at 0th time P 2 starts, then P 3 starts and then P 1 starts. Now, let us say in this particular scenario what sort of waiting time will be there? Maybe P 1 job which is there, which will be executed last job, it has to wait for this unit of a time. And how much time P 2 has to wait? Maybe P 2 started over here and it was not to wait for any other time, and P 2 it just we have to wait for only 3 units of a time. Now, in this sort of a scenario, in case I change the order of the execution of the processes, what is the waiting time over there? Maybe I get only 3 units of a time. So, what do we observe? Okay, in case of first come first served jobs, it depends upon in which order they are coming. Had they coming in this particular P 2, P 3 and P 1 order, perhaps my waiting time would have been much less as compared to my earlier waiting time, which came out to be second. Maybe if you look at my this particular case is much better as compared to the other job. So, this is what we also call as a convey effect. Okay, your short processes are behind the long processes. Maybe in case I start with, okay, let me take first short processes, then maybe I will be having all the jobs which are there for the which has got a long waiting, long CPU burst, that will be all the time waiting over there. Now, next algorithm which we have got is, that is improvement of the earlier algorithm, first come first serve basis. We say it is the shortest job first, that is whichever job is shortest, if I select out of those sort of a jobs, whichever is the shortest, I select that particular job and execute it. Now, that is what we do is, we try to associate with each job what is the CPU burst it requires, and we use this particular length to schedule the process with the shortest time. Now, again it can be a non-primitive scheduling or it can be primitive. What is a non-primitive and primitive in this particular case? In case I got a job which is executing, there is another job, once it is executing, there is another job which comes there, which has got a shorter time as compared to the job which is executing. Then if I take it out of the CPU, then we say it is a primitive scheduling, primitive shortest job first algorithm, but if we allow that particular job to execute till the time is over, we say that as a non-primitive scheduling, non-primitive shortest job first algorithm there. So, or we can just improve upon this. What is the improvement which we can have? Okay, let me say okay, my job is executing, there is a higher priority job comes over there. Then let me see, there is a not a priority job, but the length. What we do is, we try to find out what is the remaining time for that particular job. That is, let us say there are 2 units of time which is left for this, and the job which has come requires 3 units of time. Maybe then I will not preempt it, but allow it to continue. But in case my execution time which is left for that particular job is 3 units of time, the job new which has come up is 2 units of time, then maybe I will be preempting that particular job there. Maybe this is what we call as a shortest remaining time first. Maybe I will explain it. Okay, let us say we have got these jobs P1, P2, P3, P4. Let us say this job requires 5 units of a time, this requires 3, this requires 4, this requires 2, and they have come at a particular time. Let us say this particular job has come at the 0th time, this has come at the 2th unit of a time, this has come at the 3rd unit of a time, this is let us say come at the 5th unit of a time there. Let us say this was the time of arrival. Now, what will happen? Let us say this is my CPU. Now, initially let us say at 0th time there is no job which is there. So, this particular job 5 units of a time will get into the CPU. Now, once it has gone into the CPU, it will start executing, but at the second time 2 units of a time there is another job which comes over there which requires 3 units of a time. Now, how much execution has taken place for the P1 job? 2 units of a time. 2 units of execution is over in case of a P1. Now, where does this preemptive and non-preemptive come into the picture in this particular algorithm? In case I take out this particular job because that was requiring 5 units of time, this was requiring 3 units of time, I take out this particular job and bring it back, then this sort of a scheduling we call as a preemptive. Preemptive, shortest job first, but in case this P1 is executing, I allow it to execute. That means, P1 job which was executing at this particular moment, I allow it to execute. Then in that particular case, we call it as a non-preemptive shortest job first algorithm. Now, there is an improvement in this. Let us say this was requiring only 2 units of a time. Now, let us say this P1 is executing. Now, at the 0th time P1 is executing, at 2th time still my P1 was executing. Now, if I see how much time is left for execution of this particular job P1, let us say 3 units of a time, and how much time it requires? 2 units of a time. So, what will I do? I will be preempting this particular job P1 and loading this particular P2 over here. So, this is what we call as a shortest remaining time first scheduling. That is what we are comparing. We are comparing with the shortest time remaining for this particular job before we decide whether we are to preempt it or we are not to preemptive it. So, this is what we call as a shortest job first algorithms. Now, in case of a shortest job first algorithm, that gives us the minimal average waiting time for a given set of processes there, because we are going for the minimal job first. So, that way it will give you the minimal waiting time. Maybe I will show you the simulations. Let us say we have got this preemptive shortest job first. Let us say we have got these processes P1, P2, P3, P4, and they arrive at this particular moment, and these are the burst time which is required. Now, in case of a shortest job first non-preemptive, what we have got is, let us say P1 comes, we make it to execute. Now, the moment P1 is over, what are the jobs which are there in this waiting queue? Maybe it is P2 and P3. Now, at that particular moment we will compare which is the shortest out of that. Since it requires only 1 unit of a time, we will be taking this particular job into the CPU, and then next job starts is P2 because if you look at P2 and P4, maybe by this particular time P2 and P4 would, both of them would be in the CPU waiting for the execution. So, since P1 and P4 both the jobs are there which are waiting for the execution, and both of them requires the same unit of a time, then in this particular case we come to this particular aspect कि whichever job has come first, that will be there for the execution. That is the reason why we are putting P2 for execution, not P4 for execution in this particular scenario. So, afterwards it is the P4 which will be executing over there. So, same way we can calculate the waiting time, maybe for P1 there is no waiting time, and P2 there is a 6, and for the next 3 and 7 we divide it by 4, and we get 4 as the average waiting time in case of a shortest job first. And in case of a preemptive scheduling, let us say maybe this thing will be more clear here. P1 will start executing. Now, the moment P2 comes over there, it has come at the second unit of a time, it requires 4 burst time there. So, now P1 will be taken out of from the CPU and P2 will be start execution. Then afterwards P2 will be executing, then since P3 comes, it requires only 1 unit of time, P3 will be executing. Now, afterwards again P2 will come for execution, then P4, and then at the last it will be P1. So, this is what happens in case of a preemptive scheduling. So, this is the average waiting time in case I go for this sort of a schedulings there. Now, the major problem which is there in case of a shortest job first is how exactly I should estimate how much time CPU time it will take. Maybe I can estimate for the whole job, okay, this is the amount of time which will it take, but how about the bursts which will be there for the IOs and the CPUs over there. So, that is again one of the most difficult tasks which we have to do once we have to determine the length of the next CPU burst. Now, there are certain estimate formulas which are there through which we can do is, one of them is this particular thing, okay, next burst time will be you multiply alpha with Tn plus 1 minus alpha with Tn, where alpha is some constant which has got value between 0 and a 1, and Tn is the actual length of the nth CPU burst which was there. So, this is what we call as the finding out the length for a next CPU burst, or there are prediction methods also through which I can predict what will be the next values which will be there for the CPU burst. Now, if alpha is 0, what will happen? Then my Tn plus 1 will be Tn, that is my recent history does not count, okay, it will be same for all of them, or if alpha is 1, then Tn plus 1 will be Tn, and only the actual last CPU burst will be counting. Now, if we expand this formula, maybe we will get some values through which I can just find out what can be the values in case I have to estimate this, but mind it, these estimates may not be exact, because most of these estimates which we have got as a formulas there, they are the estimates through which I can estimate based on my last values there. Now, what can be the problem with this sort of a scheduling? As I said, okay, one, we are not able to estimate how much time it will take for each of the jobs as far as CPU burst is concerned. Another is the moment I go for the shortest jobs, maybe my longest jobs are the ones which will suffer. What will happen? Let us say there is one job, before it start executing there is another small job which comes, again another job, there is another job which comes over there which has got a small burst time. So, like this all these jobs having lesser time will be executing earlier as compared to the larger size jobs. So, then next sort of a scheduling algorithm which is there with us is we have got a priority scheduling. What is the priority scheduling? That is, we just define some sort of a priority for the process, okay, whatever processes are there, we define some sort of priorities, and based on the priority values we execute those sort of processes there. Now, that is what the CPU is allocated to the process with the highest priorities. Now, whichever job has got the highest priority, we will allocating the CPU to that particular process only. Now, based on the various types of operating systems, it depends upon whether the smallest integer is given the highest priority or highest integer is given the smallest priority. So, that depends upon the implementation of the algorithm, but concept is each of these jobs will have some sort of priorities which will be in the increasing or the decreasing order. Again, these jobs, this algorithm can be primitive or it can be a non-primitive. That is, in case there is a highest priority job which comes over there, whether I have to take out the existing job or not, that will depend upon my scheduling algorithm, whether it is a primitive or a non-primitive algorithm. Now, there are again some problems associated with this. We call it as a problem of a starvation. What is a starvation? Okay, maybe my low priority jobs will never get a chance to execute. That is, a process may never execute in case there is a keep on some higher priority jobs coming over there. And what can be the solution for this? Maybe aging. That is, as my jobs keeps on waiting, its priorities we keep on increasing. Maybe I will give this example. Let us say I have got this P1 job, let us say it requires 3 units of a time, then there is a P2 job, P3 job, P4 job, P5 job, P6 job, and let us say P1 arrive at the time 0. Now, P2 is a job which require let us say 10 units of a time, it came at the first unit. Then let us say there is another job which requires only 2 units of a time, it came at the again the at this particular maybe comes we are to define their priorities. Let us say this P1 has required 3 units of a time, it is let us say it has got the priority 40. Let us say we go by this sort of a scenario, whichever has got the highest priority value will have the highest priority. Now, this P1 will be having the highest priority, it will be executing on your CPU. Let us say P2, it has got a priority 5. Now, what happens is the moment P1 execution is there, P2 comes over there. Now, the moment P2 is there in the queue, there is another job P3 which comes into the queue. Now, since this has got a higher, let us say this has got a 20 priority there. Now, since this has got a higher priority than this particular job, let us say we call it as a priorities. Now, this has got a higher priority than this particular job. So, what will happen? This will have to wait and this job will be put for the execution. Let us say P3 comes for the execution. Now, while this P3 is executing, there is a P4 job which comes over there. Let us say it requires some unit of a time and there is some priority, let us say this has got the priority 30. Now, P3, P2 is waiting, but now P4 will be executing because it has got a higher priority than this particular job there. Let us say again once this is executed, let us say another job comes which has got a priority 20, again this priority is higher than this, and again let us say another job with priority 15, again it is higher than this, it will be executing. So, what will happen in this particular case? This particular job P2 which has come much earlier is suffering due to this. So, this is the problem of a starvation we call. That is, this particular process is suffering because it has got a very low priority as compared to the other jobs which are coming over there. What can be the solution? As I said, okay, as this particular process ages, based on the aging we keep on increasing its priority. That is, this is being done by the system only. The moment there is another job P3 which goes for the execution, let me say I add 5 to his priority, still his priority is lesser than this. The moment this job comes, I add let us say 15 to its priority. So, this priority of P2 will keep on increasing and ultimately at this particular stage it will start execution over there. So, this is what we call as the problem of a starvation and a solution for the problem of the starvation here. So, next type of execution which we have got is we call it as a round robin scheduling. That is, round robin is, it is based on the time sharing concept. Each process gets a small unit of the CPU time. That is, for the execution purposes each of these jobs gets this CPU time, and usually it is in some sort of a quantums there. Maybe I will be giving 10 unit of time, maybe I will giving 100 unit of a time to this particular process, and once every job it is to be given some sort of a seconds. After this time has elapsed, the process is preemptive added to the end of the ready queue, and each of these jobs they keep on getting this sort of a time there, and if there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU time in the chunk at the most q times in a unit time. So, this is what we have got as the waiting time for each of the processes there. So, this is executing like this. Let us say this is my CPU. This is usually my round robin scheduling is valid in case of a time sharing system. Let us say this is CPU, this is my terminal 1 which has got T2, T3 and T4. Now, let us say I start from here. Initially execution for T1 starts, and once my T1 time slice is over, in spite of the fact the processing for T1 is not over, it will go to the T2, and once a execution of T2 will start, and once its time slice is over, it goes to T3 and then it goes to T4, then again the turn of T1 comes and again T2, T3 and this is. So, like this each of these jobs they will keep on going for the execution. Now, the moment my job is over, when this particular time, when this will is switched off, either my time slice is over, that is the first case in which I have to go for switching over the job, or I needs a IO over there. Maybe my job as such needs some sort of a IOs there. In that particular situation, it has to switch the job from T1 to T2 over there. So, how does this performance varies? Let us say if my queue is very large, the time slice which I have defined is very large, then obviously it will reduce to the first in first out algorithm only, because let us say each of my job requires a unit of a time between 5 to 20, whereas the time slice which I have defined is 25. Then in that particular case, within that particular time, in one time slice only, this each of these jobs will be over. So, it will reduce to only FIFO. Now, if my queue is small, that is the time slice which I had defined is very small. In that case, what will happen? There will be a lot of context switching, meaning thereby it will keep on jumping from one job to the other without doing much for the jobs there. So, this is the effect. Once we have got a queue quantum of a time which we allocate to each of the round robin scheduling, which is very large or which is very small there. So, this is example of a round robin with the times quantum of a 20 unit of a time. Let us say I got P1 that requires 53 unit of a time, P2 it requires 17, P3 it requires 68, P4 it requires 24. This is how my Gantt chart will look like. Now, if you observe P1 start execution, then the moment its time slice is over, P2 start execution. Now, why it is stopping at a 37 unit of time? Because my P2 requires only 17 unit of a time, and the time slice which I had defined, time quantum which we had defined, that is of 20 units of time. So, that is why it will be finishing in 37 units of a time. Now, then P 3 start, since it requires 68 units of a time. So, it will stop at 57. Now, then P 4 will start, again it requires 24 units of a time, it will go into the next slot. Now, the moment all of them has got one turn, it will start the next step. Now, P 1 will start, because it has got still time for execution. Now, after P 1 it is a P 3 which will start execution, because P 2 execution is over by this particular time, and then it is a P 4, and then again P 1, P 3, again P 1 will come. Now, since P 1 will also be over by this particular time in the third slot, so it will be only P 3 and P 3. So, in this particular scenario, what is being done is the system keeps on checking whether it needs a time slice or not. In case it needs a time slice, it gives the time slice, otherwise it goes for the next slot. Now, maybe in this particular case, there will be higher average turnaround time than shortest job first, but better response in this particular case. Now, that is how I can calculate the average waiting time also in this particular case, by knowing at what time my job is over. Now, this is how this time quantum and the context switching time varies. Let us say my process time is only 10 units of a time and my quantum is 12. How many context switching I require in this particular case? Maybe I do not require any quantum context switching in this particular case. In one quantum of time, I will be completing my whole job, because I just require only 10 units of a time. Now, in case I have got 6 as the quantum for time, then maybe I will be having only one context switching, because after 6 units of a time I will have to shift to the other job. And if I further reduce, let us say I reduce it to 1, that is time quantum which I had defined for this particular job is only 1 unit of a time, then maybe I will require 9 context switching in this case. What does this imply? If my time quantum is 12 units of a time, if what is this particular scheduling? This is a first come first serve basis scheduling, or what I say is a multi programming sort of a scheduling, but in case it is very less amount of a time which I am defining, then maybe my context switching is increasing. What does it implies? That means overhead upon my system will increase. That is whatever are the overheads, overhead in the sense, okay, I got a shifting from here to here, here to here, here to here, everywhere there is a shifting of the jobs, and at that particular time my CPU is not doing anything. So, that is what we were saying as a overhead, and my overhead for my system will be increasing in this particular case. So, this is how my turnaround time varies with the time quantum. Okay, let us say my process P 1, P 2, P 3, P 4 are there, and this is in case my time quantum is this or time quantum is this, my this sort of execution will be, turnaround time will be varying in this particular case. So, this is what we have got various algorithms through which we can just schedule our CPU. Now, what we have done today, we have just discussed about various criteria for CPU scheduling, whereby what we want to do is we would like to increase our throughput, we would like to optimize the utilization of my CPU, but along with that I will be trying to reduce the waiting time. As I said, in first come first serve basis, we have got a very higher waiting time as compared to once I got for the shortest job first. Then we have just gone through some of the algorithm for the CPU scheduling. By this algorithm means the steps through which we can just schedule our processes on the CPU. What does it mean? Okay, whatever are the jobs which are there in the ready queue, once I have to take it to the CPU for the execution purposes, I have to take those sort of a jobs for the execution. Then we try to simulate some of this sort of a scheduling algorithm. What is the simulation? The way I have taken certain values and how my various algorithms will work in this sort of a scenario there. Thank you very much.